A very great tutor. Our group 4. Our title is Simulation for Case of Power Quality like Switch Voltage, Under Voltage, Oscillator Transit. Our group member has Muhammad Akram bin Adam, Muhammad Fahil bin Rosli, Muhammad Izzuddin bin Noor Azlan, and me, Liu Taiping, and Ye Naichuan. For the project background, modern power system rely heavily on sensitive equipment, making power quality more important than ever. Issues like voltage cell, under voltage, and oscillator transit can cause data loss, equipment damage, and system failures. This project uses MATLAB or Simulink to simulate that disturbance and apply mitigation techniques like DVRS, voltage stabilizer, and filter to improve system reliability in life with 1EEE 1159 standard. Our objective is first is to simulate three common PQ disturbance: voltage cell, oscillator transit, and under voltage. Analyze the effect of each problem on the electrical system before, during, and after the disturbance. Third, implement mitigation technique like DVRS, UPS, and filter to reduce the impact of each issue. The final is to evaluate the effectiveness of that solution using simulation result and international standard like IEEE 1159. The problem statement is the power quality issues still affect many systems, especially in critical environment. In Malaysia, awareness and research on problems like voltage cell, under voltage, and oscillator transit remain limited. That disturbance often go unnoticed but can lead to equipment failure and high maintenance costs. This project aims to fill that gap using simulation to study their effect and test effective solutions safely and efficiently.
My name is Muhammad Zudir bin Azlan. My entry number is DE22052, and today I will present about the part of the project which is methodologies. So this project follow a simulation based approach using MATLAB and Simulink to investigate three main power quality, which is voltage swell, under voltage, and oscillator transient. So we begin by identify common power quality problem in both industry and industry system and residential system. There is three disturbance by selected based on their frequency and impacts. So the commercial literature review was conducted to understand their behavior, cost, and effective mitigation method, referring to IEEE 1159 standard. So that we after we decide and after we identify, they have five. The simple power system was modeled in Simulink to constant, which is three-phase source, transmission line, linear and non-linear load, four injection component, and last but not least, measurement, scope, and mitigation block. So each disturbance was tested under three conditions, which is normal operation, disturbed condition, and after applying mitigation. So the key data is such as RMS voltage and current, waveform distortion, frequency, and THD were recorded. So mitigation method applied include DVR for voltage swell, uh, UPS stabilizer for under voltage, and Snowball circuit filter for transient issue. The effect of each method was analyzed and compared against standard limits. So
My name is Muhammad Fadil Rosli. Today I will present my part, which is about the result discussion for the under voltage. As you can see, there are around three pictures about the under voltage for the pre-PQ, during PQ, and the last one post-PQ. Okay, we will talk about the first picture, which is after you can see in this first picture for the pre-PQ situation, the Simulink model shows a stable filter system with the balance 400 volt and the system RMS around 230.9 volt, which is confirming the healthy operation without any disturbance. As you can see in the waveform is very stable without any disturbance. Okay, next we will talk about the during PQ. As you can see during the PQ, the circuit we added the LG file, which is the cost of voltage specs is around 230.9 to 210 volt. It is showing the power quality disturbance and need of other system protection. And the last one, for the post PQ, As you can see in the circuit, we add the AG4 and the VR support, which is the VR support voltage drop around 1 second to setting the time 1 second to the 2 second to recovery. Around 1 second and 2 seconds for the recovery. After the VR inject the voltage, to restore the power quality after the fault happened in the circuit. As you can see in the waveform, there are stable voltage. After that, there are disturbance. Then the stable, then they'll go back to the after 2 seconds for the recovery the waveform into the normal.
Okay, I will discuss about swell case. For pre-PQ, system operate under normal balance condition with stable 240 volt RMS on all phase. And the right side is our graph, which is stable. And this is the simulating model. During PQ, the fault on phase A and B caused the voltage set, while phase C show a slight swell. And this is the during PQ graph. And this is the simulation model. I added a fault on this model during PQ. And for post PQ, the fault cleared at 0.4 second, and all phase voltage returned to the nominal level. And this is the post PQ graph. After 0.4 second, it returned to normal voltage. Okay, that's all from me.
My name is Muhammad Akram Hamdan and my manometric is DE220112. So I'm going to continue the next part of presentation, which is the oscillatory traction. So basically, we have a three condition, which is the pre-power quality, during power quality, and post-power quality. So we go to the first picture, which is the pre-power quality. So pre-power quality, in this pre-power quality, we have a simulating models that show the stable three-phase system of distribution line with a heavy disturbance. So if we can look at the graph of waveform, we have a steady state of waveform. So this one is the normal condition. So the next one is during power quality. So the during power quality is abnormal condition, which if we need to add the disturbance. So I add the capacitor bank, contactor and capacitor bank as the disturbance. So this component will be energize the system. So we have the inrush current and voltage, and also we have we set the capacitor band to energize at the time 0.023. So if you can look at the graph of waveform, the inrush current will be start at the 0.023 seconds. So how to fix the disturbance? By adding the filter, which is inductor, we can get the stable condition or steady state condition of waveform. So by putting the inductor, we need to measure what value is the suitable to fix the inrush current and voltage to get the stable condition. So in this case, I put the value of inductor 146 millihenry to get the stable graph. So if we put it the value below 146 millihenry, the graph will be unstable. But not in like the during PQ, but the graph will be we have the voltage and current is not what we call it sequence. The peak will be one of the peak will be high and one of the peak of the current will be low. So the best value to put in the inductor is 146 millihenry. So we get the steady state condition of the graph after we fix the disturbance.
For conclusion, in this study, oscillator sensing under voltage and voltage cell in a three-phase system are simulated using MATLAB. Simulink, DVI, CPS, and filter are examples of mitigation techniques that enhance waveform quality and voltage stability. The result demonstrate the effectiveness of test method R by meeting IEEE E1159 standard. Real hardware testing and intelligent AI power monitoring should be part of future research. That is all of our group. Thank you.